Hello everyone, this is Manisai Prasad. Today I'm going to present a paper called Explaining and Harnessing Adversarial Examples. So let's get started. Uh, for today's overview, we're going to discuss the introduction of the paper, what are the adversarial examples, why do they happen, adversarial examples that's in the paper, and the equations and everything, and the adversarial training, what's missing in the paper, and how can we improve it. Let's go. Okay. The paper is called Explaining and Harnessing Adversarial Examples. It's published as a conference paper at ICLR 2015 by Ian Goodfellow, Jonathan, and Christine. This explores the phenomena of adversarial examples where a small permutation to an input can change the model's output. So, models misclassify examples that are only slightly different from correctly classified examples drawn from the data distribution, right? And that is what we call as adversarial examples. And these inputs can be formed by applying small but intentional worst case permutation to examples from the dataset, and such that the permuted input results to the model outputting an incorrect answer with high confidence. The model will be uh, classifying the input but with a high confidence. And several machine learning models, including state of the art neural networks, all are vulnerable to adversarial examples at the point of time. And in many ways, a wide variety of models with different architectures are trained on different subsets of the training dataset also misclassify the same adversarial example. For example, if I have trained one model and my friend who lives in a different place but kind of use similar dataset, or the dataset subsets of the dataset or whatever, he completely used different architecture, I use completely different architecture, but still we both have misclassified that adversarial example. We're gonna see more about these in next slides. And adversarial examples explores fundamental blind spots on our training algorithms. And why do they actually happen? The cause of adversarial examples was mystery, and speculative explanations suggested it's because of the extreme non-linearity of the deep neural networks, but perhaps like insufficient model averaging, insufficient regularization, or poorly supervised learning problem. That all comes bad. This paper shows these speculative hypotheses are unnecessary because the linear behavior in high dimensional spaces is sufficient to cause adversarial examples. This views enables us to design a fast method to generating adversarial examples that make adversarial training practical. And adversarial training can provide an additional regularization benefit beyond provided by using dropout, pre-training, model averaging, and all those, because like all those are actually right now is vulnerable for the adversarial examples. Yeah, we can generate permutated inputs using a fast gradient sign method, where we first take the gradient of the cost function with respect to input, and we take the sign of the gradient, and after that we scale the whole term using a value of epsilon. Here the theta is the parameter of the model, and x is the input of the model, and y is the target associated with x, and j is the cost function. Yeah, and we just learned the adversarial example is carefully computed to be misclassified, right? In lot of cases, we are able to make a new image that's indistinguishable from the human perspective, human observer, from the original image. Here, in this slide, we have a panda on the left side and the right side, right? And the first image has not been modified in any way, and the convolutional neural network uh, trained on that image will be able to recognize that's a panda, right? It recognizes that as a panda. And one interesting thing is that the model does not have a lot of confidence in the decision, right? We can say it's around like 58% image being panda. If we then compute the exact, if we compute that example, which with a modified optimal direction to move the pixels, like which is the part in the middle, we compute that, and it's to human eye it looks like a noise. It's very carefully computed as a function of parameters of the network. There is actually a lot of structure there. If we multiply that image of the structured attack by a very small coefficient and add it to the original panda, we get the image which is same for the human eye. Human can't tell a difference from the original panda and this panda. In fact, in this slide there is no actual difference between these two pandas. And when we present this image to a convolutional network, we use like a 32-bit floating values, and most of the monitors, most of the displays that's there, that just displays 8-bit color resolutions. So we don't have a chance to actually see those, but these 8 bits won't be affected, but it will affect other 24 bits in the floating point representation. And that little change is enough to fool the convolutional network into recognizing this image from being a panda to a gibbon. Another interesting thing is that it does not just change the class, it has the whole uh, confidence that it's the right image. See, it's like it's representing 99.3, 99.3 probability of its being a gibbon. So yeah, and this was the model that's on the ImageNet. And yeah, we can use adversarial training to make our deep neural networks more resistant to the adversarial examples. This is one example of the cost function. Here we have two parts for it. One is with the clean images, and the second one is the adversarial examples. By training the neural networks on the clean and adversarial examples, we can kind of regularize the model. Using this approach to train a max out network that was regularized with a dropout, we were able to reduce, like in the paper, the author able to reduce the error rate from 0.94 without adversarial training to 0.84 with an adversarial training. So that's there is good to have. The model also became somewhat resistant to the adversarial examples. Without adversarial training, the same model was giving error rate of 89.4% on the adversarial examples based on fast gradients and method that we just saw. And with the adversarial training, the model rate fell to 17.9%. So we can see that the adversarial training is actually minimizing the worst case error with the data has been like perpetrated by any adversary. And we were just talking about the adversarial generalization at the start of this session. That time I mentioned that I can train a model on a data, and my friend who trained the model on a different subset of the data, we both can be fooled by one adversarial example. The model will predict the wrong output, right? This is this happens because of normally explanations on suggested that it happens because of the extreme non-linearity, overfitting, because like me and the other guy was like kind of overfitting. That's what the explanations were kind of like. In both cases it failed, but to explain why multiple classifiers assign the same class to these adversarial examples, we can hypothesize that like neural networks with the current methodologies all resemble the linear classifier learned on the same training set, right? The reference classifier is also able to learn approximately the same classification weights, which are on the different subset of the training set, simply because like machine learning algorithms are able to generalize.